In the previous video we were looking at introduction to projectile motion. In this video we're going to take that further and now start to look at some problems in projectile motion and some of the equations and how we apply them. But before we do, the first thing that I want to mention here is a sort of an underlying thing to keep in mind, and something that I often forget to do and we'll sort of have to do halfway through a solution. But it basically comes back to the fact that because we've got vectors, and in particular the vertical direction, so the velocity and the displacements, it's important to define or to assign the positive direction in the vertical plane. So it's important to define whether up or down will be positive. Now there are a couple of options. You can always just have up as being positive, and just always deal with the fact that gravitational acceleration will be negative, or you can change the direction of the positive direction based on the scenario that you're dealing with. I'm actually going to go with that option. I'll change it depending on the scenario, and hopefully we'll sort of explain as we go through. If it's going up and staying up, then you'd probably have up as being a positive direction. If it comes back down to its original height, bit of a mix, you could have either. If it falls below its original height, then you might have down as being positive. So there's one of the first things to be aware of, and I'll make sure that I address that as we go through and look at these problems that we'll be dealing with. Now, as we go through projectile motion, there are a few special scenarios that we'll start off with, and we'll do the special ones first because they're a little bit easier to make sense of. And the first one that we'll have a look at is horizontal projection. So what we mean by that is that when an object is being propelled or launched, it does so horizontally. What that means is that the vertical component of the initial velocity is going to be 0. So there's no motion vertically at the instant that it's being propelled into the air. So we'll have a look at an example of that. So the scenario that we're going to deal with here, we'll have a cliff, and at the top of that cliff we'll have a cannon, and that cannon is going to fire a cannonball with a velocity of 40 meters per second horizontally. And so imagine that the question here was determine how far from the bottom of the cliff the cannonball strikes the ground. So that would be the question that we're dealing with. And when we talk bottom of the cliff, what we're really saying is what's the horizontal distance that the cannonball has travelled. So just finish that question, and as I said, the first thing to identify here is the direction that we're going to treat as positive. And I'm just going to make a little note over the side here. It's a very simple way of doing it. If we have down in this case as being the positive direction, so that's all you need to do to remind yourself and to make sure you know what the direction is that you're dealing with. A couple of other things then to note about this one as well. I should have mentioned in the question itself. We'll have the height of this cliff as being 100 meters, just to make it a nice easy example. And so from there we need to then start to look at the quantities that we need to deal with. So we've already stated quite clearly that the initial velocity is going to be 0. So we know that it's a horizontal projection, so there's no initial velocity in the vertical direction. We know that the acceleration in the vertical direction is going to be the acceleration due to gravity, and because we've defined down as positive, that means that's going to have a value. I'll just put a little positive there to remind us that that's 9.8 meters per second squared. And we know that the vertical displacement of the cannonball, because it starts at this point here and then falls to some lower point, the displacement is going to be 100 meters below where it started, and so that will also be a positive, and that will be 100 meters. The only other quantity that we know there as well, if we look in the horizontal direction, is that the initial horizontal velocity is 40 meters per second. and we know also that the acceleration in the horizontal direction is going to be 0, but we won't bother jotting that down. So basically then we know that this cannonball is going to follow some sort of path and strike the ground at some point down here. So what we're really trying to find is that quantity there, which will be our horizontal displacement Sx. Now, in order to solve this problem, I'm going to set this out the way that you really should set out your working, including these sorts of statements. So the first thing we're going to do is define the time until the cannonball strikes the ground. So that means we're looking at the vertical components and seeing how long it is in the air using those quantities that we've defined up just above. And that then means that we need to have an equation that incorporates time. So if we've got the initial velocity, the acceleration, and the displacement in the vertical direction, we can use the equation y is equal to half gt squared plus uy t. Now hopefully you can see here why this particular scenario is a special one to deal with. And that's largely because this term that we've got at the end here, so this one here, is going to go to 0. So that term basically drops out and we don't need to worry about it. So we end up then just with sy is equal to half gt squared. So it makes the solution just a little bit easier because we don't have to worry about that last term. And so we can substitute into that equation then. So we have that the vertical displacement is 100. We know that the acceleration due to gravity is 9.8 and multiply that by t squared. So if we go through the algebraic steps, t squared is then going to be equal to 100 divided by a half times 9.8. And so we can then figure out that t will be the square root of all of that. Notice that I'm not doing any intermediate steps with the calculator here. I'm just writing that all out in one big calculation so that I can use my calculator once, and that would give an answer of 4.518 seconds. That then allows us to find the horizontal distance travelled. So we've found the time that the cannonball is in the air. We now need to find the horizontal distance. And so that's then just looking at the that value Sx being equal to ux multiplied by t. And so we can just substitute straight into that, and we find that the quantities there, the values I should say, 40.0. Notice here that I'm going to substitute in the unrounded value. So that value of 4.518 is an intermediate answer. So that gives a value of 180.70 meters, which again, when we round it off to the correct number of sig figs, would be 181 meters. So that value of 181 meters is the distance that the cannonball lands out from the base of the cliff. As I mentioned in the previous video, it could have been that you might be interested in finding out what the velocity is. That's another question that you might want to have a go at yourselves, but I won't do that here, just take up too much time. Certainly something that we can have a look at as we go through some of these problems in class. The next special case that we're going to look at then deals with maximum height. And when we're looking at maximum height, what we're really saying is that we're trying to find Sy when the vertical velocity is 0 meters per second. So in this case we've got some initial vertical velocity as the object's moving, but then once it reaches the top of its flight, it's not just for a brief instant, it's not traveling upwards, it's not traveling downwards, its velocity is going to be 0 as it changes from going up to then coming back down again. We can go through that in a bit more detail in class if you need that clarified. If we have a look again at another example here, imagine in this situation we've got a say a football sitting on the ground, and and someone's kicking it. So as they're kicking it, they're applying a force to the ball with their foot, and as they kick that ball, the ball's going to start to move off through the air, and it's going to travel somewhere off into the distance. But the important thing that we're looking at here is that as it's traveling in that direction, we want to find out how high it goes to see if it's going to travel between the goalposts or above the wall or whatever the case might be. So in this case, we'll have the initial velocity as being 34 meters per second. Notice now we do have an angle that we need to deal with, and so we'll lay out the angle there, 55 degrees. And the question here might be something like determine the maximum height reached by the ball. So still using the same equations of motion, you'll notice this one, it's a little bit different to the previous question or the previous scenario, given that we're now looking at the final velocity being 0, not the initial velocity. And the first thing again that we'll need to do here is define our positive direction. Now, because we're looking at it traveling upwards, we're not interested in what happens after it reaches its maximum height. We're going to deal with the positive direction being up in this case. So it just makes it a little bit easier to deal with the direction being up, because that's the way that everything's moving. So again, we need to look at the quantities that we've been given and figure out exactly what's going on with the initial velocity. So you can see here that we've got an angle involved, so we need to resolve that so that we can figure out what the components are in both the horizontal and vertical directions. So if that's our vector u, this would be uy, and this would be ux, and so this is just the generic diagram here. So we can see that the quantity uy is going to be equal to u sine theta, and so uy, when we substitute in, is going to be 34 sine 55 degrees, and that's equal to a value of 27.85, and because it's in the upwards direction, we'll put a little plus there to indicate that it's up, so that's 27.85 meters per second. The acceleration due to gravity is the acceleration in the y direction, so that's going to be g, and because that's down, that's actually going to have a value of negative 9.8 meters per second squared. Note that I haven't bothered with ux here, given that we're only looking at the maximum height. The horizontal component's not particularly important to consider, but the final velocity, as we said, at maximum height is 0 meters per second. To find the maximum height, we could first find the time that it takes to get to that maximum height using the equation sy is equal to half gt squared plus ut. But we actually don't need to in this case, because we have enough quantities to use the equation vy squared is equal to 2g sy plus uy squared. So we've got all of those values except for sy, so that's the one that we're going to find. You'll note here as well, we can sort of make this simplification that term is going to be to 0, because we know that Vy is going to be 0 at maximum height, and that then allows us to manipulate this equation a little. So we'll take the 2gs onto the left hand side, so that becomes negative 2gsy, and that will be equal to uy squared, and the last step then is simplifying, so we can find that sy is going to be uy squared over negative 2g, and now we can just substitute straight into that equation, and we'll find that sy is equal to 27.85 squared over negative 2 times negative 9.8. Remember that the acceleration due to gravity is in the downwards direction, so these two negatives will give a positive, and so the final answer then is 39.57 meters, and rounding off to the correct number of significant figures, that would give us a value of 40 meters. Note here the value is positive, so it's in the upwards direction first of all, and secondly, this 0, if we just write it as 40, obviously it's two significant figures when we look at all the working, but we really would need to write that as 4.0 by 10 to the 1, meters to show that that 0 is a significant digit. So in the next video we'll have a look at one last special case, and then we'll look more generally at just applying these equations of motion to projectile motion. We'll do a few more of those sorts of problems in class as well.